All right, looks like we're finishing up the chapter on pointers. I think we already have the concept of pointers. You know, we've talked about them like 4 or 5 times as the days have gone by. So the point of pointers, no pun intended, is that they point, or they can point to memory, to objects, to structures that are declared outside of the function. So we have a function called multip here. We're going to use the pointer to pass back the value of the multiplication of those two. So we're passing in 2 doubles, but we're also passing in the address of the double. And so we declare this as a pointer. We declare the parameter as a pointer. We're passing this in the argument in as an address, and then we use our pointer nomenclature in order to get that. Same thing for sum array. Here we have an array. No, this isn't the same thing. We're not passing back data via the pointer, but we're passing in an array as a pointer. And this pretty much means the same thing as this. They would work exactly the same way. One is just using pointer nomenclature. One is using array nomenclature. So p array plus x, and then the star means dereference. Find the data that's stored there. It's just the same thing as doing p array subscript x. And so when we're calling our code, we'll create an array. We'll calculate the length of the array. Why didn't we calculate the length of the array up here? Because you can only use the size of trick to get the length of the array if the array is declared in the same scope as size of is called. You can only use size of if you're in the same scope where the array was declared. For arrays. Very specifically for arrays. Haven't checked to see if structures and stuff work like that. I don't think they do. Okay, so then we pass that in as the length. The size of the array divided by the size of the double gives us the length of the array. And we pass that into sum array so that we can get the summation of all the values in the array. So malloc. We used malloc. We used malloc before. The idea is that malloc will allocate a certain number of bytes. You have to calculate the number of bytes that you want to malloc. And I think we're going to do a little bit more mallocing today using structures. So, malloc, with respect to arrays, malloc needs the length of the array and the type of the array. So, the length of our array was defined as 3. The type of our array is double. And so we're going to need the length of a double is 8 bytes currently. And so we're going to need 24 bytes. 3 times 8 is 24. We will allocate, we will call malloc, memory alloc. We'll get 24 bytes back. We'll get a handle to it, but it's just a return. It's of type void star. We have to convert it to be a double star. It's just a pure memory address. It doesn't have a type. The compiler doesn't know what type it is. So we use casting to turn it into the type of the array. Then we can fill in the pieces of data and call sum array. And then we free our array. And then we set it to null. Now honestly, every time you call malloc, you should check the results. For our little toy programs that we write, we're never going to run out of memory. But after you do a malloc in real world, we should have some kind of if statement. If PDA is equal to null, we're in big trouble. We might just want to print an error message and bail out. You know, print out of memory. Ask them to hit enter and then do exit, 1. prove that there's, bail out completely. They probably can't recover from the situation. So exiting seems rude, but I'm not sure what else you would do. I guess you could let them try the operation again, and you could keep looping, and they could, go and try to kill some other processes. But if you're running in a very small environment, where a user isn't sitting there, then I don't really know what you can do besides just terminate. We've talked about this enough. You can use array syntax, and you can use pointer syntax. So const pointers. You use a const keyword if the function should not be able to change the data. This is an array, but we really don't want them to be able to change the contents of the array. So we flag that pointer as a pointer to constant memory. So if we went in through here and then something tried to change one of the values, if we did num subscript 0 is equal to 35, the compiler should catch that. So that would be a syntax error. Or this, where we declare a pointer, and then we try to change the dereferenced pointer, the value to which the pointer is indicating, to something, but it was declared as a constant, so that should be an error. So our summary. Pointers are variables that contain a memory address. Their value is an address. You put the indirection operator in front of the variable name to declare a pointer. Int star p is a pointer to type int. And then you use a unary operator to get the address of another variable. It's often referred to the address operator. Pointer variable should always be initialized with either another variable's address or with null, which is the same thing as 0. So by default, arguments are passed by value, which makes a copy of the data. Pointers let you pass in the arguments by reference, which can be speedier. Passing an array name to a pointer assigns the first memory location of the array to the pointer value. Similarly, initializing a pointer to an array name stores the first address of the array of the pointer. That's just saying that you can pass in an array, and then when you declare your parameter, you can define the parameter variable as either an array variable or a pointer variable. C just doesn't care. Print the memory address of a pointer using %p, and you use the const qualifier to achieve a read-only argument while still allowing the ability to pass in things by reference, by pointer, rather than by value, by copy. Alrighty, I know I whizzed through that pretty quickly, but it's everything we'd already talked about on Monday, I hope. Is that pretty much true? Thumbs up or thumbs down? Do we need to cover any of this more? I saw at least one thumbs up. How about you, Dan? Alrighty. Don't feel pressured. If you really want more talk on it, we can do that. Okay, this PowerPoint has some stuff on strings. I've now created the strings PowerPoint, so I need to upload a copy of this where all this stuff has been removed. But I didn't mind talking about strings during the array chapter. I almost wish that, well, strings should be talked about before pointers, in my opinion, but they didn't. It seems like you have to know everything before you can know anything. And so it's always a toss-up as to what topics you're going to hit first. And that's why I kind of like nudging up against them several at a time so that we've already hit the concept before we read about it in the PowerPoints. And it also helps if you've read the textbook. That's not the PowerPoint. This is the PowerPoint. So Chapter 8, strings. We've talked about strings a lot. Hopefully we won't take up the whole lesson just talking about strings again. I want to get to a different concept. I want to get to the idea of using structures and malloc to create objects. Alright, I'm going to fire up Sigwin. Touch July 18.c. go and open that file with TextPad. There it is, J18.c. Alrighty. Whatever. One thing we haven't talked about is to how to pass command line arguments into a C program. When we define int main, we can define it either like that, or we can put some parameters here, and those parameters get filled in by arguments from the command prompt. So if you define your main like this, just with an empty parameter list, you can't pass in command line arguments. You might be able to get out environment variables or something like that. But if you define your main header like this, and check it out. What is this right here? This is an array of arrays. Well, it's a pointer to an array. This is the count of arguments that was passed in. These would be the arguments themselves. If you are using this from a command prompt and not Visual Studio, go ahead and play along. You can configure Visual Studio to pass in command prompts as well, but I mean command line arguments as well. But yeah. So what I'm going to do is I'm going to declare main with that syntax. And the name of the arguments is not fixed, right? Because variable names are meaningless. We could call them Fred and Barney. But int argc, that's the count of the arguments. And then char star arg values, like that, a pointer to an array. You'd better not try to access this unless there really are any arguments. So we want to check argc. That's our count. Let's just print argc. Printf argc equals %d \n, comma argc. Return 0. Let's just see what that says. Might not say anything. Might get 0. So from our command prompt, gcc j18.c. And then .\. All right, we have one argument. What is that argument? We didn't give it a command line. We didn't put /a or /? Or anything like that. Well, we better print it out. The first argument will be stored at index value 0. So let's do that. Printf argv subscript 0 equals %s, because it's going to be a string, \n, comma, argv subscript 0. Why 0? Because it's the first one. If we had 2 arguments, we could print out 0 and 1. If we have 10 arguments, we could print out 0 through 9. So as we play with this idea, we might write a loop, display all the arguments. Compile it, run it. Alrighty, check it out. The first argument is the command that was given to actually launch the program. If I'd called it .exe, we'd have seen /exe. Let's run it and give it a command line argument. ./a space hello. Now we have 2 arguments. Let's print them out. Let's use a for loop, but let's start our counter at 1. Why? Because we don't really need to know the name of the program. we need to know if there's any additional arguments. So I'm going to do this. We need a counter. I is equal to 1. Or I guess I could initialize it to 1 here. For I is equal to 1, I is less than argc, I plus plus, or plus plus I. And let's fprint out that argument. Fprintf argv subscript %d in subscript equals %s \n, end quote, comma, I, our index counter, and argv subscript I. That's not how you launch it. Okay. And I closed Sigwin. Alrighty. GCC J18.c. I'm going to provide an output file name J18.exe. And what do you know? I used fprintf, which is a mistake. Fprintf sends things to the specified file handle. I could do that. I could put standard out here, stdout out, but why use fprintf if I'm only displaying stuff to the screen? Well, if I'm going to send stuff to the error stream, stdeir, then it is useful to do fprintf. Anyways, let's do that again. That was a mistake. I'll probably change that to just printf. Okay, now I'm going to run it. /j18.exe. All right. The first argument is /j18. It left the exe off. All right. It's interesting. But let's pass in an argument. I'm going to run it again, space, hello there. And so the first argument is .j18, the second one is hello, and the third one is there. And why do you do that? So that you can control the behavior of the executable. You know, just like ls. ls has got a, if I type ls space dash dash help, it gives me a whole bunch of ways I can run ls. If I do gcc dash dash help, it gives me a whole bunch of information about how to call GCC. Too much, really. If I wanted to read all that output, I could do gcc dash help, or dash dash help, and then I could pipe it with the vertical bar, the shift backslash, into the executable called more. And what more does is it's a way of displaying the information, and I could page up and down. Well, I guess I could hit spacebar. I think there are other ones which are better than more. Absurdly enough, there's one called less, which lets you use page up and page down to view all the contents. If you need lots of help on using these things, all right, how do I get out of less Q? All right, man space GCC gives me the help pages on compiler.
Yeah, 19,000.
And we get to see a whole bunch of help.
Yeah, there's 19,000 lines.
Yeah. All right, I expect y'all to have all that memorized by Monday. Maybe not. Okay, and then Q to quit. All right. So that's the idea behind command line arguments. You check argc. If argc is greater than 1, you do something with it. If it's supposed to do something with it. What if it's supposed to take a command line argument and you don't give it one? You could do something like this. If argc is equal to 1 or less than 2 or something like that, it's a problem, and you could print an error message. Printf. No command line arguments found. Something like that. Really, there was one, right? But the user didn't give any. Something like that. And you might want to exit or return or something like that, you know. Bail out. Alrighty. I did want to hit that while we're still talking about strings and arrays. Let's go get. So some of these pages are from the PowerPoint. I need to delete that, and I need to just delete all of those pages from the PowerPoint previous and re-upload that. So C does not identify strings as a data type. All they are is just an array of characters. So you can declare a string like that. You could remove the number, and it will automatically allocate enough. What the compiler does is it counts the number of characters and then adds one. So this would actually be a string of 5 characters, the last one being the 0, the null. Or you can declare it as a pointer. So getting strings from input, use scanf. It's funny that they're finally telling us that after 7 chapters of us actually using this already. So here we declare color as being 12 characters long, and we set it equal to null. We're not setting the we're setting the first element to null, so it's an empty string. You know, if you have this but that first character was null, then it's an empty string with no data. They're just doing that so that if you printed it out, you wouldn't get any garbage. And then print, enter your favorite color, use scanf. We know that %s is the data type for a string. We don't use the pointer, the address nomenclature, because color already is a pointer. We could have declared it like this, right? So we don't need to use the ampersand, although we've already proven that if you do put the ampersand there, it works. And I still don't know what horrible magic it's doing in order to get that to work. And then print, you entered that %s, so we print the color back out. This is an unsafe way to do it. Why? Because this is only 12 characters long. Oh, well, that's bad. Now it's only 1 character long. If they typed in a color that was 1 letter more, it's going to read past the end of the buffer. Is 1 character long enough to hold a string? No, it wouldn't even be able to hold a single letter. Because, you know, you need 2 characters. You need a space for the letter, and then you need a space for the null in order to hold a string. So that was dumb. I need to revise that back to the way it was. Okay, so we have 12 characters, but, you know, somebody may invent a color, you know, pale blue-green or something. That's more than, you know, dark chartreuse. It's more than 12 characters long. In which case, when this reads in, it's going to be, scanf is going to be storing byte by byte characters, but it's not going to stop at the maximum length of the array. It's going to keep going. And any data past the bounds of the array is going to be corrupted. We may get to find out about it. We may not. So I spent like 2 hours figuring all this out, and then I decided I wish I hadn't spent this time. Because there are better ways to do it. But as kind of an aside, there's a Python function called strip. And what strip does is it removes all the spaces from the beginning and the end of a string. Well, in my mind, there's a similar idea that's useful in C, which is removing the control characters at the end of a string. And why would you do that? Well, if you're reading input, you might get a carriage return, or you might get a carriage return line feed at the end of your string. A control character is one with an ASCII value of less than 32. So what this is doing is, given a string, go through it by character by character, and if we ever find a character that's less than 32, set it equal to 0. And really, we could do a break right there, rather than going all the way through, because as soon as 1 character is set to 0, as soon as 1 character is set to null, that marks the end of the string, and we don't need to keep fixing the rest of it. All right, and then I went nuts. Just for your information, the code on the following page could be written in a very cryptic form. So that and that. This is kind of absurd. I wouldn't have put this in production code, and I don't even know why I did it except as an academic exercise. So what is it doing? It's using the ternary operator, the conditional operator. It's checking to see if that specific character is greater than or equal to 32. If it is greater than or equal to 32, it returns that character so that it can be stored back into itself. Otherwise, it returns 0 so that we could replace that character with a null. So if we're looking for a specific character to remove, this is worded incorrectly, we should use STRCHR to see if the character exists. This is a far better way. If we're searching for a specific character, for example, 0A. If we go and look up at ASCIItable.com, a 0A hex is a line feed character. And why do we care? That's what we get if we use fgetS to read input. That's how it indicates that it hit the end of that particular line. So if we use fgets to read into a string, then if it hit the end of the line before the null character, there's going to be a 0A. There's going to be a line feed character. And we probably want to get rid of that character. We don't want that character sitting there at the end of our string. We want a nice string that is terminated by a 0, not terminated by a line feed and then a 0. So what STRCHR does is it searches the string for a specific character. And this could be any character. You want to find the first Z in your string, you put a Z there. You know, single quote Z, whatever. It searches this and it returns a pointer to that character if it finds it, or it returns null. Now this is different than the same functions in Python and Java and stuff like that. In those languages, if you have a string search function, it returns the index. You know, if the Z is the third character in the string, it'll return a 3. If there is no Z in the string, it'll return a -1. And C is not doing that. Instead, it's actually returning a pointer. So what I'm doing here is we're searching the string for the line feed character. And then if we find the line feed character, we set that character equal to null. But if we don't find the line feed character, then the return pointer was set to null, and we skip it. So this is the fastest way, the easiest way of removing a form feed, or excuse me, a line feed from your character, from your input string. A lot easier than doing that. So why did we show the strip code? Because fgets is safer than stdin. Scanf does not limit the number of characters. The user could type 8,000 characters, overriding 8,000 bytes in your RAM. So more data may be read than will fit in the array. Array overrun and data corruption will occur. Fgets, on the other hand, lets you specify how many characters to get. Like this. You declare your name. You display what's your name. And then we use fgets to read it in. But since our array is 60 characters long, we're going to specify 60. It occurs to me that maybe we want to specify 59 because we want to make room for the terminating null. It occurs to me we might want to specify 58 because we want to leave room for the terminating null and a terminating line feed. I would have to play with that. What happens if you have exactly the right number of characters? Maybe we will. And then let's strip the control character. That's using this loop to strip the control character, all the control characters out. I really would just rather do this now that I've thought about it. Let's go ahead and play with that. Let's declare an array of a certain length. Char sc name. And I'm going to allow only 10 characters for my name. Set it to an empty string, which is the same thing as they did when they did this. I'm not sure why they used that syntax. To me, that's clearer. Alrighty, and now let's ask the user for something. Just for grins, I'm going to use fputs. I'm going to display a message. Enter your name. Now I'm going to use fgets to get our name. Excuse me for coming back and cheating to make sure I have the syntax correct. Alrighty. Fgets, the way it works is you specify the string to read into, the number of bytes to read in, and then the input stream, the file handle. Now std is our file handle for reading from the keyboard, from the console. So fgets, our string name is szname. I want 10 characters. And I'm going to read from stdin. I goofed on this fputs. On fputs, you have to specify your output, your file handle. If you were writing to a file, it'd be a different file handle, a file that you yourself opened. But we're just going to use stdout, which is the standard console output. All right, just to test it, make sure we got what we wanted to get, let's print out our name. Name entered was single quote, %s, n single quote, \n, double quote, comma, szname, parentheses in parentheses. Wrong. Get lost. All right, let's compile it. GCC J18.c. Now to run it, /a. No command line arguments found. Well, what do you know? Did I not save it? Cat space J18.c. Yep, there's all my data. GCC J18.c, and I am going to specify a file name. -o a.exe /a.exe. What is it doing? It's not running my changes. Oh, it's bailing out here. Print, no command line arguments found. Dumb. Remove that return -1 if you put it there. Alrighty, now there'll be, I could just run it again with provide a command line, but I'm not gonna. Alright, enter your name, Bob. The name entered was Bob. But check out what it printed. Quote, Bob, line feed, end quote. We don't like that line feed there. We're going to want to trim it at that line feed. Let's try entering more than 10 characters. Our array is 10 characters long. I'm going to run it again. My name is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 characters long. And there we got 1, 2, 3, 4, 5, 6, 7, 8, 9. What's the difference between the way it behaved here and here? Do we see a difference in the output? I mean, besides the fact that one is Bob and one is the numbers. Yeah, the quote is on the same line, meaning that when it read in this data, it didn't read in the line feed. Why? Because it didn't get to the end of the data here. It didn't read in A, B, C, D, E, F. It did read in enough to fill our buffer and leave a space for the null. Now we have another problem now. And our problem is that this data is still left out in the input buffer waiting to be read. So if we do another fgets, we're going to get the rest of that data. We could prove that to ourselves. I'm probably going to comment this out, so I don't care if you do it or not. But I'm going to copy this statement and that statement and just paste them. I guess it doesn't take long for you to do a copy and paste. Compile it. Run it. Alrighty. 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. You see what it did? It filled in both of my return values. It didn't stop and let me type in anything else because A, B, C, D, E, F and the line feed were still out there waiting in the buffer. Maybe that's okay. Maybe it's not. Maybe I would like to ignore everything past the certain amount. So how could we tell whether there was any additional data waiting out there or not? If there's a line feed in it, we know that we didn't get it all and there's some other stuff hanging out in the buffer waiting to give us problems. So then the question becomes, how do you ignore the rest of the line? Ignoring that problem, let's remove the line feed if it does exist. So we're going to use STRCHR to search for that string, that character. How do we know what that character is? Well, we could print out the ASCII values of each one. We don't absolutely know that it's a hexadecimal A. You're just taking that on faith. Let's find out exactly what it is. I'm going to delete those two lines now. But I'm going to use a for loop. Int I for I is equal to 0. I is less than 10 because that's the length of the array. I plus plus I. And now printf %d because we want the ASCII value of it. Space. Well, that's probably enough. Yeah, space, end quote, comma, and then SZ name subscript I. End parentheses in semicolon. And then let's print a new line to get us to the next line. Because we don't have a \n at the end of this. I just want to print all the characters on the same line, all the ASCII values on the same line. Or I could get an error. All right, I'd already defined I somewhere up there, apparently. And I did that again. On my other machine, I have it configured so if I hit Control 3, it actually runs the compiler. So I keep trying to do that here out of habit. All right, enter your name, Bob, and here's what it prints out. B-O-B followed by 10. That's decimal 10. What if we wanted a hexadecimal values of those? Instead of doing %d, do %x. So go over here and change that %d to a %x and run it. Or, recompile. Jeff. J-E-F-F, and then the line feed character. So we're going to search that string. If we find the A, we're going to remove it. If we don't find the A, then it means that there's more data out in the buffer. So let's use string to find it. Not string. We're going to use string character. So what am I going to call it? I guess I'm just going to call it test. But it is a pointer. Char star test is equal to strchr, search my name, SC name, for a 10 or an OXA. They both mean the same thing. Find line feed. If we have it, we're going to remove it. So if parentheses test not equal to null, we have it, and we're going to set test equal to null to terminate our string there. Else, let's just print a little message saying that there's more data in the buffer. Maybe we're not going to even take the time to handle that right now because I'm still kind of itchy to move on to other topics. It's like this is important stuff, but conceptually, using structures in malloc is probably more important. So, if test was equal to null, oh, and by the way, that should have been uppercase letters, my mistake. If test is equal to null, we're going to print out, look out, there's more data in the buffer. \n, end quote. So if I type in something longer than 10 characters, I want to see that. Actually, it's going to be longer than 9 characters, I think. That would trigger it. Because the 10th character is going to be a null always. So if we say bring in 10 characters, it's really only capable of bringing in 9. I believe that to be true. I'm going to try it out. Compile it, run it, enter your name. I'm going to type in 10 characters. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's 10 characters. And what did it get? It got 0 through 8. And notice there's no 10. There's no A here. I was expecting it to do something slightly different. I was expecting it to print that message. Okay, I never saved my file. It's useful to save your changes. Yeah. All right, let's try that again. Compile. And what do you know? I didn't include string.h, so I don't have strchr. I got to go back up to my includes and add string.h. # include string.h. Now once more with feeling. All right, enter your name. First I'm going to just type in Bob. It didn't print a message out. It did strip out the A. We just don't have any proof of it because we didn't print it out after we stripped it. We should fix that. But in the meantime, or beforehand, I want to run it and I want to give it too much data. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's 10 characters and it's only going to read in 9. Since there was no line feed, it knows that there's more data in the buffer. And so if we call fgets again, or anything else that's going to read from the file, that's going to cause havoc. So we need a way to wipe out all the remaining data in the buffer. And I think I'll just say that there's a slide that shows how to do that. But I do want to print out the buffer after it has been trimmed, just to show that it was. So I think I'm just going to move this print statement down here underneath all that stuff. And maybe this print statement too. All right. At least we'll see that the hex value A was removed. The line feed will now be gone. Bob. And maybe it is, maybe it isn't. Did I not save it? Still there. Alrighty, I'm just going to go and steal this from the PowerPoint then. I'm going to take this code. Well, really this should have worked. Is that not what I have? I do not want to get bogged down on this. That code looks exactly the same to me. Zero XA, 0x0A. Maybe that's it. Maybe I need to prefix that with a 0 there to get that to work. That can't be it. Could be. That's probably it. That was it. What do you know? All right. So it worked. All you got to do is change your code to be 0x0A. Then it'll work. I'm going to skip the part about skipping the rest of the buffer. It's here in the slides. So one of the problems of using fgets is that if there's more data than specified as the number of bytes to get, the rest of it will still be waiting out there at the file handle, or STDIN. It just goes to the end of the line. That's what fgets is supposed to do. You may need to scan the string for that control character, and if it is not found, it means that there's extra data waiting. Here's a way of handling it. This code right here would handle it if you're reading from STDIN. I haven't checked it yet to see if it'll work from reading from another file handle. It wouldn't take much time to copy and paste that, but I'm just going to skip that for now. All right, so our string functions. We've already talked about these. String cat will append one string to the other. String ling returns the length. All it does is it counts all the spaces, all the characters before the null. String lower will turn all the letters in it to lowercase versions of the letters. So it just checks the ASCII value of it, and if it's within a certain range, it adds 32 to that ASCII value to turn it to a lowercase letter. Why that? Because that's the difference between a lowercase a and an uppercase a. 65, 97, they're 32 different. So all it has to do is, if it's between the range of 65 and 90 inclusive, it adds 32 to it to get it to be over here. And then vice versa. If you use the lowercase version, it'll check to see if it's between 97 and 120 whatever, and then subtract 32 from it. String copy, string compare, string rev, and here's our new one, string CHR, and I need to add another new one, string string. We're going to talk about that one as well. Searches a string for a string. Remember that the way STRCHR worked is you passed in a string and then you passed in a character, and it returned a pointer into that string if that character exists in it, otherwise it returned null. String works the same way. It searches string 1 for string 2. If it finds it, it returns a pointer to the occurrence of string 2. Otherwise it returns null. Same idea. I'm skipping slides that I'm sure that we've already talked about. We know that string copy and string cat are dangerous because if the resulting string is too large to fit into the target string's array, memory corruption can occur, will occur. So incorrect use of scanf. Scanf requires an array, not a pointer. This would blow it up, or at least it wouldn't work, shouldn't work. If you just declare color as a pointer, the way that we have been doing, and then you do this, it's not going to work. It needs an array. We could force it to be an array, you know, doing that or whatever. But if you're going to do that, you may as well just declare it, right, however big you want. Then you're ready to go. If you feel like it, you could set the first character equal to null, so that if you printed it out before you read anything into it, it would print out as an empty string rather than garbage. I need to undo that so that if I upload these notes back, it's not incorrect. Okay. So you can use arrays to contain a list of strings. And we just did that in our code up here. This char star argv is an array of array. It's an array of strings. And so the next two slides discuss that. Char star string names 3. Now we have an array, or a pointer, to 3 strings in a row. And if we want to, we can print them out. There are functions for manipulating individual characters as well as strings. If you want to turn an individual character uppercase, you pass 2 upper to it. And what it does is it makes sure that it's within the range that's acceptable, and if it is, it adds, subtracts 32 from the ASCII value. Otherwise, it doesn't touch it. You're not supposed to do anything with it if it's a number, or punctuation or whatever. You can't make an uppercase 1. And so this code right here duplicates the functionality of string upper, and it's worth looking at. Remember that I put stuff in these slides that aren't in the book. So I do recommend looking at the slides carefully as well as the book. Examples of string copy. String. Search a string for a string. It's very useful. More specifically, string takes 2 strings as arguments. It searches the first string for the occurrence of the second string. And here's how it's defined. Of course, in the C library, it's not called haystack and needle. But, we're searching this string, haystack, for this string, needle. Those are just variable names. They don't matter. So the parameters, the first one is the string to be scanned. That's our haystack. Needle is the substring to be searched to find within the haystack string. And what does it do? It returns a pointer to the first occurrence that matches the character's needle. They have to be an exact match. So here's a function that uses string to return the index. If you're a Java programmer or some other language where you have string functions that return index values, like C#, then you may wish you had a function that would search a string for another string and return the index. That's the way Python works. I forget the name of the function, but you can search a string in Python for a character or another string, and it'll tell you the index position at which it returns. So what does this do? It calls string. It looks for the needle in the haystack. If it doesn't find it, it returns -1, meaning I did not find that. Otherwise, it calculates the index, and the index is just the difference between what it found and your starting address. Like if the starting address for the string is at 1,000 and it finds it at 1,004, well, the index is 4. Just tuck that away. The idea that you can write your function, and there may be a library function that already does that, to treat the string in the same way that you're doing it in Java or Python. Here's an example of using string. We declare 2 strings. Haystack says, "Hello darkness, my old friend," because we're a Disturbed fan, or Simon and Garfunkel. And we're looking for the word friend in here. And so we call string, and we store its result in a pointer. And if that pointer is null, it means we didn't find it, and we print friend not found. Else we calculate the index, and we say that %s was found at index %d. And we could type that in and run it, or you could take it on faith. I want you to have this idea, though. So just because we're only spending 2 minutes on this slide, please understand it. This is not stuff that's in the book. Here's one that's very specifically not in the book, and it's very, very important. Maybe it is later. SCANF. That stands for string scanf. It works just like scanf, but it converts data from a string rather than from standard I/O, from standard input. It works like this. You give it a string to process. Then you give it the formatting string. Then you give it the arguments to fill in. So if we do this, scanf, and we search this string looking for a floating point number to convert, then when we run it and we print it out, we're going to see 123.456. Now when I tested it, it was 123.456.001. That's floating point weirdness. It can't store 123.456 exactly in the floating point IEEE specification. Why is that? Because it's stored in binary, not base 10. And whenever you convert decimals from base 10 to binary, you may wind up with values that can't be stored exactly. That would be infinitely repeating values, just like 1 divided by 3 is 0.333. So you get a floating point error there. And floating point errors can be devilish to try to handle. If we were going to print it out, I would just print %.3f or something like that. And then it would print 123.456. Let's play with that. Let's at least make sure that we know how that one works. Let's play with this command line argument. Let's let them type in a number, and we're going to pull the integer out from that number. Maybe not. Maybe that's too complicated. I'm just going to come down here, and I'm going to declare a string, char star sznum is equal to 1, 2, 3, 4, 5, 6, and then I'm going to type in a word, Fred. But it's going to ignore the word Fred when we use scanf, unless we use %d space %s. Now let's declare a number to read that in to, int inum. And let's use scanf to parse that string and pull that number in. So scanf, please read sznum, parsing it, looking for the first integer. And store that into the num variable, the address of inum. And then we better print it out to make sure we got something good. Printf inum equals %d \n, end quote, inum. Alrighty, save it. Relaunch Cygwin. GCC J18.c /a. Enter your name, Bob. And it read that my inum was equal to 1, 2, 3, 4, 5, 6. And if I wanted to get that out as well, Fred, I would use %s to read it in. So %d space %s, passing in inum in our sz name buffer that we'd already declared a while back. So now that we've printed out inum, let's print out the name as well. Inum is equal to that. Sc name is equal to %s \n, end quote, sc name. And when we run, it's going to print out that inum is equal to 1, 2, 3, 4, 5, 6, and that the name is equal to Fred. So scanf provides us with a way of turning string data into numeric data. There's other ways too. The book tells you to use A2I, A-T-O-I, which takes an ASCII string and turns it into an integer, or A2F, A-T-O-F, to turn it into a floating point. That's great, but what if the data is more complex than just one number? What if it's 3 numbers in a row, right? What if it's a line of data that we read from a file, and it consists of a person's name, and then their user ID, and then their password? We'd like to be able to break that up into 3 strings. handle each one separately. And so we would use scanf. We'd read it in with fgets to get that entire line of data. Fgets is safe, so it won't crash if the line of data is too long. And then we use scanf to pull out the pieces of data that we care about.
What if something is alphanumeric in the text?
Let's find out. I'm going to put an A there, and it's not going to be right. Or, you know, maybe I'll just reverse these. Fred space that. It does the same thing that scanf does if you give it bad data. And if you haven't been testing that, well, I haven't been testing it either. So let's find out. Enter your name, Bob. All right, here's what it read in. inum is equal to that silly thing, and name is still equal to the last thing that name held, which was Bob. So how can you tell if it worked or not, if it worked successfully? Good question. C library scanf. Let's see what it returns. On success, the function returns the number of variables filled. But on the case of an input failure, before any data could be read, EOF is returned. So let's store the result of scanf into a variable just to find out if it returns anything strange. Okay, so int, I don't know what I'm going to call it, retval is equal to scanf. And I'm going to print out retval. Printf retval is equal to %d \n end quote comma retval. And what we are curious about, firstly I want to see what happens when it works successfully. It should return 2 because it turned 2 pieces of data into variables. Let's make sure that's the case. Okay, so it did successfully parse, pull out inum and scname. Now I'm going to goof it up. Fred is going to be my number. I put that in. We have badly formatted data. Let's compile it. Let's run it. Retval is 0. We found out that it failed, that we have a formatting problem. So what I would do, if I was being careful, is I would do this. If retval is less than 2, because we're trying to fill in 2 pieces of data, then we have a problem. Let's print an error message. Printf badly formatted data \n. Else, let's go ahead and play with that stuff, that data that we got. And let's run it. I want to see that error message happen. Badly formatted data. Good. So I knew something went wrong. Does that answer your question?
Yeah. I just put letters in between 1, 2, 3, 4, 5. I took out the first grade and I put letters in between 1, 2, 3, 4, 5.
Like 1A, 2B.
Yeah.
All right, I want to see what that does. It didn't tell us that it was badly formatted. inum is equal to 1, and name is equal to A2, B3, 4, 5. Well, that's interesting, and I'm not sure how to handle it. I'm just going to throw my hands up in the air and say I don't know how to handle that. What we could do is we could search the string for a space. No, that wouldn't do it. We could use %s to read in a string, and we could use in %s to read in the second string. And then we could check to see if this was all digits before we tried to convert it to a number. That'd probably be the best approach. So if we did something like this, I'm gonna undo it. But scanf scnum, comma, %s space %s, comma, and then string 1, string 2. Then I could test S1 to make sure it was a valid number. Mm-hmm. And if it wasn't, then I knew that there was a problem. Because in this case, S1 would equal 1A, 2B, whatever, you know. And then Fred would be stored in S2.
But can you specify how many characters
I bet you can.
it should take for the...
Yeah, you should be able to use formatting characters for scanf, for scanf, or for fscanf. %s and pull in 19 characters. %7d would pull in 7 numbers for the string. Excuse me, for the integer. All right, now just note that although we're not talking about files yet, there's fscanf and there's fprintf along with fgets. Now we did use fprintf one time in the code. We just printed out the standard out, std out. I was getting problems using fscanf for my input when reading from stdin, so I gave up and stopped trying to come up with slides about it. We'll get back to it when we're working with files. Like I said, your professors found that mixing scanf and gets with fscanf and fgets causes problems. So I just use fgets and then scanf to pull my data out of that string. And then we have a summary. I'm going to skip the summary. You're capable of reading the book about summaries as well as I am. I want to use malloc to allocate some structures. Before I skip on, are we okay to get to the next topic? Okay. We need a structure to play with, though. So, struct fraction. And it's going to have a numerator, and it's going to have a denominator. And we're going to do a type def just to make it easier to use. No, we're not. No, we're not. Okay. So let's create a fraction. Struct fraction f1, and then f1 dot numer is equal to 1. f1 dot denom is equal to 2. Notice that dot syntax. If you've done Java, you're very used to that. If you've done Python, then you've seen dot used occasionally, like to call functions that are attached to strings or, you know, whatever. You're going to see something a little bit weirder in a minute. Let's create another one. Struct fraction f2 is equal to, and let's fill in that data, 2, 3. I'm not sure how often I would actually use that syntax, but you can. And when we're done, numerator is going to equal 2, and denominator is going to equal 3. Now I'm going to do a type def just because I'm tired of typing that word struct. Why? Because in C# I didn't have to. So type def struct fraction, and then I'm going to make fraction with a capital F, like that. So fraction space F3 is equal to 3/4. Anytime I want to access the numerator, I'm going to do the variable followed by the dot followed by the member. Unless it's a pointer. That's when it starts looking different. Since Java doesn't support pointers, and neither does Python, then you won't have seen this alternate syntax. Let's declare a pointer to that fraction. Fraction star PF3 is equal to the address ampersand of our fraction. Now I want to print those values out, or calculate the result of them, or something. So double ratio is equal to PF3, and if I do dot, that's incorrect. So it's going to be PF3 arrow hyphen greater than numer. And then ratio equals ratio divided by PF3 hyphen greater than denominator. You see the difference? If this was a variable, I would use the dot. Now I'm going to just copy that code and I'm going to rewrite it in the other syntax. And I think I posted a notice about this. I'm going to call this one ratio 2. But I'm going to use pointer dereferencing, and then I actually get to use the dot. So asterisk star PF3, not asterisk, parentheses star PF3 in parentheses dot numer. And then down here I'm going to change this the same way. Parentheses star PF3 end parentheses dot denominator. Which syntax do you like better? I don't know. Honestly, I never really saw that one out in the wild. This is how everybody does it. So this is the one that I'd like for you to use. I just want you to have it tucked away in your head that you can always dereference something and then use it as the variable that it's pointing to. So let's print that data out. Printf denom equals %d, numer equals %d, ratio equals %f, backslash n, quote, comma, f3 dot denom, comma, f3 dot numer, comma, ratio. Just as kind of a sanity check, make sure that all this is working. I haven't compiled it in several minutes. Alrighty. And it blew up. Alrighty, when I put this code down here about string S1 and string S2, I never commented it out. I'm just going to delete it. If you get that error, delete that line about S1, S2 if you typed it in. If you didn't, great. Now back up here. All right. Did I not compile it? Oh, I still have an error. Ration. Somewhere I spelled it with an N. Oh, right there. Okay. I hope you didn't type ration. If you did, delete the N. All right, compile it. How many times do I have the word ration in it? Twice. And this should be ratio 2 is equal to ratio 2 divided by PF3. So I goofed on that line too. I was definitely not taking care enough. This line should be ratio, not ration, equals ratio divided by denom. This line should be ratio 2 is equal to ratio 2 divided by denom. Alrighty, and so the denominator was 4, the numerator was 3, and the ratio between them was 0.75. I know I'm not using the term ratio correct in that sense, but good enough. Alright, so we see how to declare fractions, but sometimes you want to allocate memory for the fraction. You don't just want to create it. You want to create the memory for it. Are we good enough, or do I need to help with typos? Have I botched y'all up yet? Okay, so I'm going to create a pointer to the fraction. I guess I already have a pointer called PF3. But anyways, fraction star pfrac1. And how big is my structure? So I'm going to do size t, which I think is just an unsigned int, equals size of a fraction. Nope, I'm going to make it lowercase. Yeah, uppercase fraction. Otherwise, I'd have to make it, everywhere you see uppercase fraction, we would have to replace it with struct lowercase fraction. Just makes it a little bit easier to type it so that we don't have to use the word struct everywhere. Alrighty, now we can allocate it. pfrac equals malloc, except I'm going to have to cast it. I guess I'll add the cast at the end. Parentheses. Oh, I forgot to create a variable name. Size underscore t bytes is equal to size of fraction. And then pfrac equals malloc bytes. But I have to cast it to the correct type. What is the correct type? It needs to be a pointer to a fraction. So parentheses, fraction, star. In parentheses right there. So pfrac equals parentheses, uppercase fraction, star, in parentheses, malloc bytes. Did we have to declare the size in a separate variable? No, we could have just done size of fraction right there. We're only creating one fraction, so we're not doing any of that business of 1 times the size of the fraction as opposed to 2 or whatever. If we were creating an array of fractions, we would actually want to do that. Find out if that compiles. Warning, incompatible implicit. Well, okay. I forgot to include stdlib.h for malloc. I got to go back up and add one more include. Up at the top, # include, angle brace stdlib.h. Close or save it. Going back down here just because. Attempt the compilation again. Really? Oh. I misnamed my variable. My pointer was called pfrac1. And then here I called it pfrac. surely it's going to work now. Alrighty. I didn't print anything with this. So I'm going to assign some data to it. We're getting close to the end of the class, so I'm not going to actually print the data out or whatever. But P, it's a pointer. So which syntax do I use? The dot or the arrow?
Arrow.
Correct. We use the arrow. pfrac1 arrow numer is equal to 4, and the denominator I'm going to set to 5. pfrac2 arrow denom is equal to 5. When you're done with it, you should free it and set it equal to null. And as I mentioned before, anytime you call malloc, you should check its results and make sure you actually got that memory. So before I start doing this, I should check. I should check to see if pfrac1 is equal to null. And if it is, go into a panic. If pfrac1 equals null, all caps, then I'm going to printf out of memory \n in parentheses semicolon, and then I'm going to exit with an error code of -1 or whatever. Now after I'm done assigning that data and I do something useful with it, I would need to free it. So free pfrac1. Why does it say pfrac2 there? My mistake. We don't have a pfrac2. pfrac1 arrow denominator is equal to 5. And then free pfrac1 in parentheses in semicolon. And set it to null, just as a security measure. So if you try to access it later, it will be a blatant error rather than a hidden one. pfrac1 equals null. Again, I'm introducing this stuff before we hit it in the book. We're getting close to the end of the semester, so next week we're definitely going to read the chapter on structures in memory management. But I already want you to have seen it before we hit it. Make sure that works. Yeah, and I didn't put any output there. Guess I could. Ratio is equal to pfrac1 denom or numer divided by double or parentheses double. We have to convert it to a double at some point, or else it's just going to do integer division and round it down. Double pfrac2 arrow denom. Then print that out. Printf ratio equals %f \n end quote comma ratio.
You don't have a pfrac2 though.
Right, I don't have a pfrac2 and I keep making that error. pfrac1, pfrac1. Thank you for catching that. All right. Expected a semicolon. Or expected no parentheses there. I need to delete that parentheses. If you typed it, it's because I did. You need to delete it as well as me deleting it. All right. And the ratio of that last one was 0.8. So we successfully created a variable. We successfully created a structure and filled it full of data by mallocing it. That's like doing class A is equal to new A parentheses in Java, except that does a lot more. It calls a constructor, you know, does things like that. Same idea though. And Java has garbage cleanup, garbage collection. meaning that when a variable falls out of scope, it cleans it up. It releases all the RAM that object was occupying. C absolutely does not have garbage collection, so you have to free the memory yourself. And in a little program like this, would it be a problem to not free up the 20 bytes or whatever of that structure? No, it would not. But if you had this in a loop that ran 10,000 times and it wasn't freeing that memory every time it allocated, you know, then it'd have 10,000 structures that have been allocated and never released. It'd be kind of fun to write an infinite loop that kept allocating RAM until we ran out of RAM. Let's see if we can do that. This will be the very last thing we do, and then it's the end of the class. Okay, so I want I'm going to just do while 1. This is going to run forever. All right, so I'm going to create an array of integers. Int star pi, pointer to an array of integers. Pi is equal to malloc. I'm going to get 10,000 integers at a time, times size of int. I'm going to check to make sure we got it. If pi is equal to null, then print an error message, printf error, and then exit -1. Else, I guess, print a dot, just so that we can see something happen. Man, I'm not going to even do that. I just want to see it run until it prints that error message. And if it takes forever, then we'll worry about putting some kind of print message there. We never free the data. Taking a while. It finally ran out of RAM. I wonder how many times it had to. How many bytes? Well, let's find out. We're going to declare a variable outside of it, and I'm going to make it a double so it can grow infinitely long. Well, not infinitely. Called bytes used. It's equal to 0. And each time we successfully allocate, so I'm going to add an else clause. Else bytes used plus equals 10,000 times the size of an int. And then if we get our error, let's print out how many bytes have been allocated. Printf bytes allocated equals, it's a double, so %f \n end quote comma bytes used. Neat. How many bytes is that? That's 1,000. Let's go over 3 more. That's 1,000,000. If I'm reading this right, it allocated 29 gigabytes. I find that very difficult to believe. But maybe it's using virtual memory or something. We managed to run the program out of memory, though. Obviously, in this kind of program, on this kind of machine, where we have huge amounts of RAM and huge amounts of resources or whatever, then the memory leak is not going to kill us immediately. But like I said, Firefox was notorious for having memory leaks, and that it would eat more and more memory as it ran, and eventually, if you didn't kill it by the end of the day, you'd come back and it'd have used up a gigabyte of RAM or whatever. It's interesting to me. Alrighty, we need to conclude the lecture. We're past our time. I really did not create any notes for today. I also did not have homework prepared. So what are we going to do? We're going to do some string functions. Ask the user for their first name. Ask the user for their last name. I would prefer you to use fgets and strip out the line feed character for both. then print the message, or then create a string with the data, I am pleased to meet you, comma, end space, end quote. You create that string named message with that data, and then use string cat to append the first name, then string cat a space, and then string cat the last name. So when you create your string, it better be long enough to hold their first name and last name on it. So not only 20 characters or whatever that is, it better be 40 or 50 or whatever, you know, some comfortable extra space. All right, then print the message. Okay, so string cat first name onto message. String cat the space onto message. String cat last name onto message. Print the message. Convert the message to uppercase and print it. Convert the message to lowercase and print it. Then print, then search the string using string CHR or string for a Z, and if a Z is found, print Z is found, else print no Z is found. Okay, that ought to be enough. Covers most of the concepts we talked about. That makes sense, guys? Pretty much doing what we did in class? Okay.